All right, I think I'm gonna get started. So, yeah, as a note, the project is due March 17th. That's this Friday. I just put up the Gradescope submission for it. So basically, what you'll want to do is you'll want to go into your Jupyter notebook, and you'll want to go into Print Preview, and then just print it out and save it as a PDF. So this just makes it like you can open it up in Preview or something like that, however it looks like. Just save it as a PDF, and it should give you this nice output like this. So this is just one of the notebooks that I grabbed for today, but you can do it with any notebook that you choose. And just submit that PDF, and you should be good. Put a bunch of diagrams. It'll just look better. Awesome. Cool. All right. So today's lecture is going to be on k-nearest neighbors, and then the Bias-Variance Tradeoff. So those of you who've taken who's taken Data 8 before in this class? So most of you have seen KNNs, right? The ones who've been taken Data 8, right? Okay. Yeah, so it's a pretty simple machine learning algorithm. It's pretty good in terms of, well, relative to its like simplicity. Training time is really great. You literally don't have to do anything. You have your data and your training is done. Just collect data. Test time, it's a little bit more complicated because the algorithm works by just measuring distance from the test point that you have and then the existing points in the data set. Yeah, so then what you do with all these nearby points. So the k-nearest neighbors algorithm, I'll take a step back and explain it from the basis. So the k-nearest neighbor algorithm basically finds nearby points in the space of like of your data set, of your training data set, that are close in like what we call Euclidean distance, or really any other distance metric. But just a notion of just like closeness goes on when we try to figure out like what proper points are close to your test point, you could say. And so when we find all these nearest points, we find the k nearest points. What we do, we have each of these points have their own label. And so we take these labels, we aggregate them somehow. So we likely just use them as like a voting mechanism. And then we return the most common label among all of those. So let's say we're classifying like x's and o's, actually pluses and minuses in this case. We have our test point right here, which is in a k equals 3 nearest neighbors scenario. So the 3 nearest neighbors are these 2 plus signs up here on the left, and then this 1 minus sign. And because we choose to aggregate by voting, so basically we choose the most common label as the label of this point becomes a plus. Are there any questions about this algorithm? It's fairly simple. Cool. So it's really great. It's super simple. So like you can whip it up in like no time at all. When you get to bigger data sets, it becomes a little bit more problematic. But again, there's libraries for handling huge data sets and everything like that. Again, as I mentioned earlier, training time is super fast. It's basically 0. And furthermore, it doesn't really make any assumptions about the structure of your data. So if you remember from linear regression or logistic regression, there's a certain kind of structure that those models handle really well. So in the case of like linear regression, basically it handles effectively just linear data really easily. But when you start getting into stuff that's a little bit more noisy or maybe a little bit more like oscillatory, then your model kind of breaks down and you start underfitting to those. Now KNN, you can find the right parameters that will give you the right balance between underfitting and overfitting, because you just play around with the k parameter. What's up?
You just use this for classification.
You can actually use it for regression. It doesn't really matter because you know this aggregation method here, right? So instead of let's say this was a regression problem instead, we could literally just take the average of all these values here, and that would give us the regression label for this point. Did you have another question?
Yeah, how is it different than like clustering?
Then clustering? Okay, yeah, I'm gonna bring that up in a second too. I can just explain it to you real quickly though. The difference is that clustering is unsupervised, so you don't have a notion of label. You basically just say like, these points are all close to each other, these points are also all close to each other, and these points are all close to each other, so I'm going to put them in their own respective groups. Now with KNNs, you already place the groups like in their own labels. You don't do anything special like assigning distances from each other. You basically say, okay, I have a point, let's say I have like some clusters here, or like a cluster of points here. This is KNN whatever situation, and I have a test point that's like right here. I probably will assign it to the labels that belong here because it's so close to this. And I won't even care about these labels because I find that all of the nearest neighbors are just here.
So essentially it's very nearly the same except for the fact that it's labeled versus unlabeled.
It's very similar in that they like use the same kind of distance metric between all the data points, and there's not really like any crazy things like modifying parameters that you'd see in like linear and logistic regression. But the difference is, yeah, you do have labels in k and n's, and k means you don't have labels. Yeah, so back to the topic of k and n's. A cool thing about k and n's is that they actually appear outside of machine learning in a bunch of different areas. One example, which is not my own, it's from Professor Efros. He gave a pretty great lecture on it in CS 189 last semester, is the U.S. court case system. So basically, what lawyers will do is if they're trying to evaluate what kind of decision should be made for a specific case, they'll go back and they'll look for other court cases that have existed in the past. So let's say we have a decision on somebody committing like manslaughter from 1989, and a judge has to determine whether this person who drove his car into another person and ended up killing them should be tried for murder or manslaughter. So they may look at this like manslaughter case here, and they may consider this murder case here, and then they want to figure out where this new case lies. So maybe we say like, oh, the driver had ill intent, so he'd probably be closer to this murder case. Let me just write these out. So it may be closer to this murder case. However, if they did it by accident or they weren't paying attention or something, probably much closer to a manslaughter case, something like that.
So how do you define distance usually, like in general for k-n's?
It's for k-n's, it's actually really up to you. So there's a bunch of different metrics you can use. The most common one is Euclidean distance. So Euclidean distance is effectively what you've seen with like triangles and everything like that. So let's say we just have like a simple vector like x1, x2, x3. The Euclidean distance is literally like the vector between 2 points in like a three-dimensional space.
Okay,
So you can take like the norm of this vector, because that could be like say we have 2 points in space. You can just take the norm of that vector, and that's your distance. So that could be one metric. Now, I don't know about any others at the top of my mind, but I know there's a bunch of others that you can use in place. What was your next question then?
So just basically to clarify, so in k-n's you have sort of your input like x's, and you also have your y label associated, and then you find sort of the minimal Euclidean distance usually, or like you just find the minimal distance between whatever your set of like your vector is and like those, and then based on that you just set that label to yours.
Pretty much, yeah. So let's say it's just k equals 1. So maybe like in this example, so we just find the nearest neighbor. Yeah, we would literally just grab like manslaughter in that case, or we'd grab murder in that case.
So if you want to average more values, you just use more k.
Yeah, exactly. And well, it depends what you want to do exactly in your aggregation method. Now you can really choose, and it depends on the problem as well. So if you have discrete values, so let's say it's like categorical manslaughter or murder, then like you can't really average that, right? You typically want to just choose the one that's like, let's say you had a field of choices and you were doing like k equals 2 or something. You'd probably want to vote based off of the nearest points rather than choosing the average. But you get the idea, I think. Yeah.
So if you have like really big data sets,
Yeah.
like huge data sets, then for calculating the Euclidean distance stuff, you have to iterate through all the training samples, right? Is there a better way to do it than just iterate through all the training samples?
Yep, there totally is. So what you can do, so I did this on a recent project. We use this this algorithm this library called NearPy. And so what they basically did is I think it's called like hash distance functions or something like that. So you can use like hash tables to get around the fact that certain data points you don't really need to access to determine that they're not near you. So we can think of it like this. Like, let's say we have our test data point here, and we have a bunch of like relevant data here. Whatever. And this is probably where it belongs, but like let's ignore that for now. And then we have a bunch of pretty much irrelevant data here. And so on. Like, we definitely know that we want to probably explore here to determine all the nearest points here first, versus going into here. So another way of doing it is literally sectioning off this space. So it's like, okay, what section should this point belong to, and then search in there. If it doesn't fit within this section, so let's say we just split this in two very simply, we could be like, oh yeah, it probably belongs in this space because the point lands in this space, and so we check all the points that land inside of this space. Now, if we get closer to like edge cases and everything like that, there's certain special handling you can do. Yeah, but as I mentioned before, there's another method where you do like hash tables and stuff like that, where you can somehow figure out the distance function based on where you land in the bins, the hash bins, I guess. I can link that in these slides later on if you'd like. Yeah. So there's like a bunch of libraries for that. Any other questions? So with k and n's, you can actually create a decision boundary similar to what you could do with linear classifiers. So as you can see here, we have our yellow category and our purple category, but our data points are kind of mixed together. So in the k=1 case, we see a little bit more of a wild decision boundary because there's a lot of mixing in between the yellow and purple points, and so there's this concept of like a noise in the data itself, because a lot of the classification that you would do with just like a regular linear boundary would cause a lot of error when you're evaluating on the training set. But it's possible that that noise is introduced from a bunch of different sources. Like maybe you have noise from your measurement or something like that. Let's say you're measuring temperature and your thermometer is like really bad. That could be additional noise that's added in. Or you just happen to have some crazy quantum fluctuations or something like that. That's just another source of noise. Basically, the world is filled with a bunch of different, like, the terms I've heard before have been like signals and noise. And what you receive as somebody observing this data is the combination of the two. I'll get more into this in a second. Does anybody have any questions about this particular image? So could anybody tell me what's happening in the first, on the image on the left? Overfitting, yeah, exactly. So what's happening is we're basically trying to determine, this is a nearest neighbors, like k=1. This is just the nearest neighbors classification. And so what will happen is the decision boundary will be drawn pretty sporadically, and then all the points near this like decision boundary, near this like center diagonal, are probably going to have a lot of testing error when we go into test time. And what do you think about the one on the right? Yeah, I'd agree. So, I mean, I'm glad nobody said underfitting. So, yeah, because this is pretty clear that it'll probably generalize really well. There's all this noise that you can see in these extra yellow points that are on the in the purple boundary, and then all the purple points in the yellow boundary. It's kind of ignored, which is nice. And so, as you can see, you can you basically start underfit. You can end up going to like k=50, and you probably will start ending up being like super underfit. And again, the underfitting overfitting trade-off is always apparent in these kind of classifications. Any more questions about this? Cool. Okay, so I've linked to a few resources regarding the k&n algorithm. So I would recommend reading or watching Professor Efros's 189 lecture on k&ns. It was really good. He's a great lecturer. Additionally, I linked to, I think, a paper on neural networks for image classification. Or sorry, not neural networks, nearest neighbors for image classification. Oh. Any other questions before I move on? Cool. So as Rishi brought up, k-nearest neighbors seems really similar to k-means, but you have to keep it clear that like they're totally different. The names are similar, but like the algorithms themselves are particularly pretty different. So as I brought up last time, k-means is unsupervised. So an example of k-means would be on the right, where we're just trying to find these clusters. And then k&n is supervised, so we have labels, of course. Same diagram as before. Kind of just like a quick enumeration of everything. K&ns don't need training. K-means needs training. K-means effectively is just finding like clusters of data. K&n is just trying to label stuff, and so on. All right. So the next subject I want to talk about during this lecture is the bias and variance trade-off. And so we talked about underfitting and overfitting, as well as just regular like generalizable machine learning models. And if you noticed last time, we have these terms variance and bias. So these are pretty key to determining like different factors that can appear inside of your machine learning model when you're training it. And they're pretty important to know and know how to identify when you are training your machine learning algorithms. So yeah, what we'll typically see in conjunction to these underfitting and overfitting terms is an underfitting model will typically have a high bias, and an overfitting model will typically have a high variance. So before we get into this, I want to talk about that noise, the noise plus signal thing I mentioned really earlier in the lecture. So what our data typically looks like, or what our data is when we're dealing with like a supervised classification problem, is we have a label y. It's passed, or it's calculated from some function f. You can think of this function as the world, the environment that you're dealing with. And you take in your data, your features x. You're like transforming them in the world, whatever. They're somehow interacting with the world. And then you have an additional noise from like quantum fluctuations, or from like reading errors, or just from human error, or any other number of sources of just extra information that just gets in the way of your readings. So what we try to do in machine learning is approximate a function h that takes the role of this f function here. So we have like a hypothesis for how the world should run, or how this certain process should run. And we want to make that hypothesis as good as possible. So in bias and variance, what we basically are trying to do is model, like for this diagram in particular, what we're trying to do is land right in the bullseye. So you can think of the bullseye as like the function f that we want to approximate. So a good hypothesis h would ideally just land directly in there, and all of our predictions would be inside of that center bullseye. Now, at the bottom left, we have a case of high bias and low variance. So that means that our predictor is like pretty consistent based off of the data that we feed in. It's like pretty good. It gets into the relatively the same areas, but what it'll be like very far off from the ideal target.
So it's like consistency versus accuracy.
Yeah, exactly. So a high bias, low variance model would be this linear fit right here. So it's pretty consistent depending on where you travel along the line. However, as you notice, it's like also pretty consistently off from the like actual generalizable model. Now, in a high variance situation, we're like pretty close to the center. We're pretty close to the hypothesis, and we hit the hypothesis at many different points, as you can see, like by the number of points that hit the bullseye here. But we also get a bunch of these extra noisy parts. So what effectively is happening is our hypothesis is fitting to the noise that we receive. It's seeing all this extra error in the data that we received, and it's thinking that's like relevant features that we need to consider, when in reality that's just getting in the way of our proper prediction. And finally, what can happen is we just fail on both ends, and we get high bias and high variance where we're really far off, and then we're basically overfitting to the noise. We're basically fitting noise more than the actual function in this formulation that I showed earlier. Any questions? Right. So basically, you could summarize bias and variance by these two definitions. So bias is effectively just the error of the model not being able to fit well. And then the variance is just the error due to the model fitting to random noise. So identifying bias and variance is like a very, very key part of being a data scientist or machine learning practitioner. So the two sources where you can actually look to identify your bias and variance are the training error and the testing error, or from last time, the validation error. So the training error reflects bias. So basically, you know that if your training error is really high, that means you have a lot of bias in your system. So if you remember the linear model, you're going to see a lot of training error because you're not able to fit all of the points really well. Now testing error reflects both bias and variance. What this means is, if you remember from the overfitting examples, we can have really, really low training error, But we can have really high testing error because what happens is we start fitting the noise of this training set. And so the testing error will be relatively high. And so what you can do to diagnose what is actually happening in your model is see which error is greater than the other, or which error. I really just compare the two errors with each other. So if training error and testing error are relatively equal, you know that you'll probably have a high bias and maybe have high variance. That's really unclear. What you could do is just tackle high bias first. If you have low train and high test, that just means you have high variance. Your model is too complicated and you are overfitting. And then if you have low train and you have low test, you're killing it. You've got a great classifier, you're doing well, you're going to make a lot of money, or you're overfitting, like who actually knows. You could be overfitting to that actual test data. So that's always something you've got to consider. You may be overfitting to the test data itself, but you can identify overfitting in at least your subset, your data subsets, by just looking at the training and testing error. So just keep in mind the things that I talked about last time. What's up?
Does that still apply when you do like k-folds cross validation? It'd be the same idea,
Of like whether you overfit and everything like that?
No, not bias and variance. It'd be the same idea, right?
Yeah. So actually, the k-fold kind of gives you a better idea of whether or not you are or like what your bias and variance are in your model, because they give you like an average, an expected value almost of like what shows up in your data. Are you taking 70 right now? You're not. So in 70, you'll kind of get introduced to like probability theory and stuff like that, and like expected value. Maybe you've seen it before. But basically, when you run, so in the case of machine learning, if you run the k-fold validation, you're basically trying the same algorithm, like the same training algorithm 5 times with your set of hyperparameters, and so you have a better idea of whether or not you're going to start creating these extra biases or variances in your data because you have like multiple iterations. So it gives you a better idea that your hyperparameters actually would yield to this result rather than it being a result of your random initialization. Because that also could be a source of like these extremities. Since you are dealing with basically a random system when you start out, but the more iterations you do, the more confident you can be that your results are true, I guess. The numbers you see are accurate, I guess. Does anybody have any more questions? So we can model the bias and variance trade-off with these set of curves here. And so as you can see, we have our bias curve, which as the model gets less and less complex, or like starts off less and less complex, you'd expect bias to be really high. So in our simple linear model, bias is really high because it is a relatively simple model. It doesn't have enough parameters to fit all of the data that we need. Now, as we increase the model complexity, say increase the degree of a polynomial that we're trying to fit to some data, we'll see the bias drop, but then subsequently we'll see the variance start to rise as well. And eventually there's a point where the variance starts exceeding the bias. And that's problematic, of course, because once we get to that point, then the validity of our model starts to drop as well. And so what we can consider is the total error of our model is, so I'll just write it out here. It's simply a function of your like variance plus your bias plus just extra error that you really can't get rid of. Because this error is basically just always present because the world is noisy, and so you can never get rid of this. But once you accept it, you can realize that you can just deal with these two variables and reduce your total error as close as possible. And so this is represented in this graph right here. So this total error graph is minimized basically when bias and variance are equal to each other. Yeah. Any questions about that? And so what you can do in this case is you can run k-fold validation at pretty much different levels of model complexity, get the data points for the bias and the variance, and plot those, and then just find the minimum of this total error graph.
How do you calculate the bias and variance?
There's a formula. I don't remember it off the top of my head.
Okay, so you just use some.
Yeah, exactly. So Yeah, as I mentioned, you can use cross-validation to diagnose whether or not you have bias and variance. So just use k-fold. It's fairly easy with like very simple models. So k-n's, you can just run cross-validation over and over again. In terms of like a machine learning system, you could probably be done with this in a day once you set up your algorithm and everything like that. So that's relatively fast. Again, if you're overfitting, just make your model less complex. If you're underfitting, make your model more complex. And then just use cross-validation on your training and validation sets to confirm whether the desired changes actually produce better results, more desirable results. Reduce your total error, rather. And here's the k-fold diagram again, for your pleasure. And so now that you've been introduced to bias and variance, can anybody answer which states have high bias, or could potentially have higher bias, or the highest bias, rather? Which parameters produce the highest bias? The 25 one? Does everybody agree? Yeah, it's the 25 one. So as the model is like relatively non-complex because it's weighing all these different options whenever it tries to make a classification. It seems a little counterintuitive, right? Because you see k equals 25 and you think, okay, that's like a higher parameter, and so you'd expect that there's a lot more calculations that go into it. But in reality, that just dampens the classification that we choose, and thus the model is technically less complex in that case. Now, so what side has the highest variance? Yeah, exactly. So the highest variance, it's going to classify pretty much any point near to the nearest point when we find it. So if we get near this like boundary right here, through the diagonal, the classification error is probably going to be very high, and as a result, our test error is going to be very high. So generalization error is going to be really high as well. And so there's another link here for more math. And then the quiz is at the end of the slides. If anybody has any troubles connecting to the slides, then let me know. That's it for the lecture. So in the GitHub repo, I've included two Python notebooks. So there's an example of how to use KNNs. So this is from last semester's lecture on KNNs. It's pretty worth going through. I don't know if these dials are just images, so you can't really do anything with them. But then it just shows how you can implement KNNs. I think. Let me see. Is this okay? Yeah, this just uses the KNN library, but also you can just implement it really quickly too. So you have this Euclidean distance function right here, which you just use for all your distances. And then prediction is fairly easy. So, yeah. Additionally, I have this Bias-Variance Notebook, which I recommend you go and test out. So you have to fill this out yourself. You have to fill out splitting the dataset into a train test split, and then evaluating a KNN model using the cross-val score. Actually, I can just do this in front of you guys real quick. I think. If I remember train test split. Okay, let's see. So what you can see here is in this data set, what is it? I think it's the iris data set. Yeah, it's the iris data set right here. And we're basically taking the first two features and we're just running KNN classification on them. And so you can see as we raise our K parameter, we greatly decrease the variance in the model. What was your question? Yeah, I think so. Let me see what it looks like if we do different parameters. What would it be? Do like. There's a way to do this. Forget. Yeah. So if you choose the last two features, they're not that interesting. And so I think these are just the two more interesting features in the data set. Now, realistically, you can't just like grab two features. A lot of the time, you can't just grab two features and do this. But I guess this is also a statement on what features are important. Because as you saw before, yeah, so this could be really a statement on like feature selection. So certain features are going to give you a better prediction than others. And the way to test that is just to run cross-validation on which feature, because that basically is another hyperparameter you can deal with. So if your cross-validation results show that the set of features that you choose, that one set of features it has a better test accuracy than the other, then you can use those set of features. By the way, I realize I use test accuracy and validation accuracy pretty interchangeably. Typically, when I say test accuracy and like fitting on the test accuracy, I always mean the validation accuracy, because you don't want to fit on test accuracy. You always want to separate your data set, keep that test accuracy out there, ignore it until you want to deliver your model, and otherwise you're just going to run into issues with overfitting to that test set, and your generalization just goes down. Cool. So yeah, basically we run the KNN algorithm in like 5 different sets of parameters, or 7 different sets of parameters. And then what we do here is we run cross-validation. Yeah, so just run cross-validation here. I think. Oh, no, wait, hold up. Oh, no. So this is a different section. So this section kind of explores cross-validation with respect to the images dataset, the one that James was exploring a few lectures ago. So what we can do, we have our data set loaded into X and Y. And so what we first want to do is split this data into a train test split for our testing. So we take, let me just make sure. This is no good. I forget how to use this. So I think it's like XY, and then you do like X train, Y train, X test, Y test. But I'll have to check if this doesn't work. Oh, I messed up. Cool. So I think this should be proper. And just as a test, we just do this. Print out the shapes. Cool. Yeah, so this looks about right. So we'd expect only one dimension in the Y values, and then 2 dimensions here. So the features are the second dimension in the X train, and then the first dimension is just the number of data points in that data set. And so what we can then do is import this function called cross-val score, which basically allows us to evaluate a model based off of a score that it outputs. Let me see. So I think you run cross-val score, you pass in like a model that you initialize. Let's see. Do like Canon. See what this does. By the way, if you use Shift Tab, you can see the argument. Okay, perfect. So what this does, it outputs a what is this? Yeah, I guess it outputs 3 different values for the classification score here. And so I made a little function here that will take the mean and the standard deviation of this cross-validation score. So what you can do is you can just test out a bunch of different scores. And so for I in like, let's do this, 1, 2, 5, 10, 25, 50. Actually, for K, whatever. And then we can do print K equals 4.
So generally, you don't want to use all the features. You only want to use a subset of features.
With the dataset?
Yeah.
Generally, I mean, not generally. I guess in kind of like the old school machine learning, yeah, definitely you would want to play around with the different feature sets and to see which one is best. In deep learning, you kind of just like throw it in. So the times have changed, but like still kind of applies. Let's see, xtrain. Sorry about that. Oh no. Okay, so we calculate this cross-val score, and then you can pass it into the CV stats, and it just gives you the mean and standard deviation. And so there's just like a quick run through of different parameters, fairly simple. And as we can see here, we run our cross-val score on the 5 different sets or 6 different parameters for k nearest neighbors, and we can see our average. I think this is test accuracy right here, and the best model for this case is going to be k equals 1. Which is a little deceptive. I wonder if this is. Oh, okay, yeah, I guess k equals 1 works best for this case.
What's CV stats?
CV stats is just a function I made right up here. Basically, so if you saw up here, the cross-val score will output 3 different values, because I think you can. I wonder where you can change this parameter. 3. Yeah, I'm not exactly sure. I forget exactly how this function works, but it gives you these 3 different numbers, and then I just aggregate the values so that they're easy to read, instead of just having to read like a bunch of them. And so it just gives you the mean and standard deviation. And then what you can do here is, if you wanted to evaluate a bunch of different parameters, you can do that fairly simply by just iterating through a bunch of different values. This is called grid search, I believe. So like a key, I guess, trick to use in doing like parameter search, hyperparameter search, is basically go by order of magnitude. So as you can see here, maybe I could do something a little bit more regular and just go by powers of 2. So that I hit like a wide number of parameters. But this gives you like a better idea of the better parameters, because then what you could do is just find the best in this set, and then go search around that singular value. So I wonder why. Let's see what that says. Okay, yeah. So I guess the best value still is k equals 1. It's kind of weird to me. Whatever. Yeah. And so you can do the same thing with the logistic regression, and then linear regression, which is just the ridge classifier, and so on. Then I guess I could just go over this as well. There's this thing called a confusion matrix. Basically, I'm just going to ignore this. So I have the solutions. Oh wait, hold up. Oh, CV. Oh, okay. Here, actually, it's made a lot of sense. So if we go back to the cross-val score, we can actually modify the number of cross-validations or number of folds we can use. So cross-val score basically just gives you all the values you'd get out of a k-fold cross-validation. So you can set CV equals to a different number, and if we look up here, change CV equals 5, we can change that to the number of folds that we get. And so this is just evaluations on the validation set of each fold. And so I think this should give us a better idea, hopefully. Nope, okay, never mind. So I'm still pretty dubious about this result with k equals 1. So something else is going on here. Maybe it's just how the cross-validation split occurred. No. Oh, okay, actually, here's another spike. So sometimes what can happen is your data, the way it's split, can actually encode extra noise into the system. So if you ever run a result and you're like ready to release this result, the best thing to do is shuffle your data and just run it again just to confirm that it isn't a result of like how the data ended up, because just randomness will always creep into your results. So just shuffle and just eliminate randomness by just running multiple trials, like in any respect that you can. So back to confusion matrices. I'm gonna cheat. Go to the answers. Something else is going wrong. So what a confusion matrix basically does. Oh man. So what a confusion matrix basically does is it. Where is that? Oh man, this is moving around. So it just kind of shows you what mistakes the model will make. So it'll basically show the predicted label, I think, on the y-axis, and then the actual label on the x-axis. Oh, okay, so rather, it's a true label on the y-axis and predicted label on the x-axis for a data set that you input. And then ideally, if your classifier was perfect, you'd have only values on the diagonal, because that means it's a correct prediction. Now, what can happen in a lot of different cases is that you get a lot of mistakes. So in this case, we have a true label of 9 that gets predicted as a 5. So this is the digits data set from sklearn. So what can happen is, yeah, so like 9s can occasionally be predicted as 5s. 8s predicted as 3s, 9s predicted as 3s, and so on. So you can just identify where your model fails. And so what you can do is go in and just do some extra data cleaning steps, maybe, or adjust your model to attack those specific cases a little bit better. Say, like, add a regularization term or something. Basically, this confusion matrix just gives you a tool to diagnose where your model fails, rather than just looking at like a test accuracy or training accuracy. Any questions about that?
Can you release the solutions?
Yeah, I'll just post them afterwards. So, because I don't know what I was predicting. What?
Oh, are you predicting the type of model or something?
Are you predicting what?
What that
I think it's, no. This is still digits. I think. Maybe we could whip it up for. We could probably whip it up for the iris dataset. If we wanted to. Let me just save this real quick. I'm curious. It's running everything. Oh wait. So okay, if I were to do this with the iris dataset, so I'm just gonna run the confusion matrix thing with the iris dataset. Is first thing I want to do, I input my x and y, and then I can just do the train test split. And y test train test split x y, very simple. And then I fit on the training set. And then get my predictions out with clf.predict. So pretty standard. And I get test predictions. And I think that's all I need here. Yeah. See how that does. Okay, so I guess this is a little big. Maybe I can adjust this. Let's see matrix. Okay, whatever. Yeah, so basically we have our confusion matrix here for the iris dataset. So the category 0, I'm not exactly sure which one that is. It has a pretty good confidence. It's not confused at all. However, between the second and the first, or the index 1 and index 2 categories, we have a lot of confusion. So you see that this box right here is pretty, it's very colored. So that means that there's a lot of mistakes in this area. So again, it's just a good way to determine where you're getting some false, I think it's false positives, false negatives, all that stuff. And it's a better tool to diagnose rather than using training and testing error for when your model is failing. So that's it for this lecture. If you have any questions about this, come up and talk with me now. Actually.
This is not related to this, but is there a link to the project? Is there a link to the Kaggle submission?
To the Kaggle submission?
Yeah, like where.
Oh, Will Song. Do you know where the? Do you know if we put that up in the project? No, just the Kaggle submission. Did we put that up?
Oh yeah, I gave the Kaggle link to
If it's not in the, is it not in the PDF file?
I don't think so.
Okay, yeah, so we still have to add that. Okay, wait, you have it? Do you want to post it in Piazza? Wait, is there anything in Piazza?
Yeah, there's
Okay.